Have you ever stopped to think about why getting gas out of the ground is so much more complicated than getting oil? I mean, you'd think a fluid is a fluid, right? But it turns out gas plays by a completely different and way more difficult set of rules. So today, we're going to break down exactly what makes gas wells such a special case and explore the seriously ingenious tools engineers had to invent just to make sense of it all.
So here's our game plan. First, we're going to see why gas is such an unruly fluid to begin with. Then, we'll pull back the curtain on the clever pseudo-solution engineers came up with to tame it. After that, we'll dive into a classic whodunit, skin versus turbulence, and see how you can pinpoint the real problem. And to wrap it all up, we'll look at the ultimate performance test for any gas well.
All right, so the whole problem really starts with the nature of gas itself. You see, the standard engineering playbook, the one that works perfectly for oil, well, you can pretty much toss it out the window here. It just doesn't apply.
Look, with a liquid like oil, things are simple. Key properties like how thick it is, its viscosity, and how much it squishes, its compressibility, are pretty much constant. They're predictable. But gas? Oh, gas is a completely different animal. Just think about it. As the pressure drops when it flows to the surface, that gas expands like crazy. This means its viscosity and its compressibility are all over the map, completely wrecking the standard mathematical models that engineers depend on. It makes a simple analysis basically impossible.
So, what do you do when the fluid itself just refuses to cooperate? Well, if you can't change the fluid, you change the math. Engineers developed this absolutely brilliant workaround. Think of it as a kind of mathematical translator to make all that unruly gas data behave just like predictable liquid data. And this, right here, is the hero of our story: pseudopressure. It's a mathematical function that takes all those messy, pressure-dependent changes in gas properties, the viscosity, the compressibility, all of it, and bundles them together into one single elegant term. By using it, engineers can straighten out the math, which lets them use their standard liquid-based toolset on this incredibly unruly fluid. This is the perfect way to think about it. Pseudopressure is basically a universal translator for our equations. It takes the complex, tangled-up language of gas and converts it into the simple, straight-line language of a liquid. All of a sudden, the chaos starts to make perfect sense. You know, before we had modern computers that could calculate pseudopressure in a snap, engineers had to use these rough approximations. At really low pressures, they'd use one formula. At really high pressures, they'd use another. But in that huge middle ground, nothing really worked well. This just goes to show how essential a complete solution like pseudopressure really is.
Now, pseudopressure doesn't work alone. It's got a sidekick called pseudotime, and it does the exact same job, but for the time axis. Especially in tight reservoirs, where you see these massive pressure drops during a test, the data can get really distorted over time. Pseudotime cleans that up, straightening out the squiggly lines on the graph so engineers can get a truly clear and accurate picture of what's going on.
Okay, so we've managed to tame the fluid's wild properties with our pseudo-tools. Awesome. But solving that problem only reveals a new mystery. Engineers were seeing this significant extra pressure drop right near the wellbore, and it was seriously hurting production. The big question was, what's causing it? And this is the million-dollar question. Is this extra pressure drop caused by actual physical damage to the rock, what we call skin, or is it something else entirely, just pretending to be damage? Getting the answer right is absolutely critical. And it turns out, a lot of the time, the culprit isn't damage at all. It's turbulence. See, normal, slow-moving fluid follows a nice, predictable path. Engineers call this Darcy flow. But when gas comes screaming towards the wellbore at incredible speeds, it creates this chaotic, turbulent mess called non-Darcy flow. And that chaos creates its own resistance, an extra pressure drop that looks almost identical to real physical damage.
So now we have two suspects, real damage and turbulence. And we have to be able to tell them apart, because the fix for one is totally useless, or even harmful for the other. What we need is a diagnostic tool.
And that tool is this elegant little equation for pseudoskin. So S prime is the total effect we're measuring, the whole problem. And it's made of two parts. You've got S0, which is the true skin from physical damage. That part's a constant. Then you've got the dq term. This is the part caused by turbulence, and here's the key, it changes depending on the flow rate, Q.
This simple relationship gives us a fantastic way to figure out what's really going on. The process is so elegant. You just test the well at a few different flow rates, measure the total pseudoskin you see at each rate, and then you plot those points on a graph.
And that graph tells you everything you need to know. If the line starts way up high on the vertical axis, that means you have a big S0, a lot of constant true damage. The fix for that is probably an acid job to clean it up. But if the line is really steep, that means your problem gets way worse as the flow rate goes up. That tells you your turbulence factor D is the real issue. The fix isn't acid, it's adding more perforations to give the gas more doors to come through, slowing it down and calming that turbulence.
Okay, so now we know how to diagnose a well's problems. But how do we measure its ultimate strength? How do we figure out that single most important number that defines a gas well's true potential?
That number is called the absolute open flow, or AOF. The best way to think of it is as the universal power rating for a gas well. It's the theoretical maximum rate the well could possibly produce if there was absolutely zero pressure holding it back. It's the ultimate benchmark.
Now, to get that AOF number, engineers run a special procedure called a modified isochronal test. It's this carefully choreographed dance of flowing the well for a bit, shutting it in, then flowing it at a higher rate, and so on. Each step gathers another precise data point we need to map out the well's real potential.
All that test data gets plotted on a special log-log graph. The final, extended flow period, is the really important one. It gives us the true performance line for the well. From there, you just extend that line all the way out to the theoretical point of zero back pressure. And wherever that line hits, that's the well's maximum possible flow rate. That is its AOF.
So, at the end of the day, it really all comes back to translation. By using these pseudo-tools to translate the unruly language of gas, engineers can slice right through the complexity. It lets them not only diagnose the well's specific problems with incredible precision, but also measure its ultimate fundamental strength.
When you think about it, these pseudo-tools are just a really clever mathematical lens, one that was designed to find clarity in the middle of chaos. And it kind of makes you wonder, right? Where else, maybe in finance or biology or even social sciences, where else could we invent new mathematical translators to solve other unruly problems?